Okay. We're going to be talking a lot about chapter 2 today. Matter of fact, we're going to blaze right through chapter 2 today, and we've actually talked a little bit about chapter 2, and you've grappled with a little bit of chapter 2 in the homework, number 2. There's going to be homework running right after lecture, homework 3. And it's not too ginormous, but it will be ready for you, and it will be due, as I've mentioned before, at 10:30 a.m. on Thursday. It always comes due at 10:30, the very next lecture. Okay, so now a couple things just about grades and updates and so forth. I uploaded early registration bonus points again, so now you've got hopefully 3 of them. But a bunch of you are on the scoreboard up here, and that is great. Also, homework 2, of course, is down here. And I want to point something out to you that in past semesters has been the bane of my existence in terms of web courses. And that is these gray rectangles down here at the very bottom of the grades page. They're completely erroneous. They have nothing to do with our grading scheme, and used to be you couldn't turn, and actually they're still there, but now they're pretty much turned off. And you may have noticed that you had like over 100% on some of your categories, bonus point activity and homework. And every semester people get all up in an uproar because of that. Hold on a second. One, two, three, four, five. You guys, everybody back here, I don't want you back this far. Everybody in the first 5 rows. Just take a minute to move your seats. It's just 1 meter of displacement. On exam day, it's going to be helpful for everybody to be in this position, so that's why we're going to try to discipline ourselves to doing it. Is that easier? Is it? Great. Oh, I'm serious. We usually get people that have a guitar to do a sound demonstration, musical notes and stuff like that.
Sure.
Have you ever had music theory class?
No.
Yeah. Are you a music major?
I might switch, but right now I'm not.
Okay. Are you a freshman?
I am.
Newbies. Newbies everywhere. Especially the people that sit in the 6th row back. Anyways, you're not in trouble, but just try to remember to do that. And that'll be helpful. Anyways, these stupid gray rectangles, in my class, don't pay attention to them. And hopefully it's turned off and permanently turned off, in which case I will rejoice, because it misleads a lot of students. They get all in an uproar. Oh, Dr. B, how can I have, like some semesters, the way it works, you can get like 14,000%. And the students come up and say, well, Dr. B, how can I have a grade of 14,000%? And of course, the answer is, Web Courses knows nothing of our grade scheme, and for that reason, 14,000% is, out of town. All right, questions before we continue? Very good. First 5 rows or closer. Very nice. Okay, let's keep going. We're going to be talking about free fall today, Galileo. But before we get to that, let's just do a little teeny recap. Last time we talked about distance polygons. We had some document cam work. We sketched velocity graphs and a kind of a general velocity graph that wasn't a straight line, either slanted or horizontal, but kind of a curved velocity graph. And the answer to how you handle that is break it up into a bunch of little teeny trapezoids like this. So for an accelerating object, like what we have here, between initial, go ahead and sketch this. We're going to kind of take it apart here. V subscript I, that's the initial speed, initial velocity in this graph. VF, V subscript F, that's the final velocity. And it's speeding up. And what we talked about last time was the fact that our strategy was to interpret the area underneath that red line segment, the velocity graph, and there it is shaded in green. We interpret that as the distance traveled by this particular object, which happens to be accelerating, for this time interval. So between time t subscript I and t subscript f, here's on the, if you look down at the time scale, the initial time is here. So this could be like 2.1 seconds. And then t subscript f could be like 2.2 seconds or some other sequence of times. Anyways, the area between those two times is the distance traveled between those two times for this object is that green area. And what we talked about last time is how the technology that we had already developed. So this is how NASA looks at complex spacecraft motions and any other physical system that's in motion. They make a zillion little trapezoids, but we handled it because we already had the technology for the distance triangle and the distance rectangle. All right, so we busted it up. Here's a little line segment right straight across from the initial velocity value, and that kind of forms a distance rectangle. That's good. And above it is the distance triangle. So yeah, we just break those out. Here we're exploding them outwards. And then you tackle them individually. All right? And so you compute the area of each of those sub-polygons, those sub-areas, and you're good. All right? And the formula reflects that. Now we're going to put together that formula for free fall in just a second. But here's the pair of formulas that we talked about last time. The first one is the distance triangle formula. For some acceleration a, 1/2 at squared. So in this diagram, t would be replaced by the quantity t2 minus tf minus ti. And in the distance rectangle, it's just d equals vt. And in this one, again, you could write down the symbol t being represented as, in this diagram, tf minus ti. In other words, a delta t. So these are kind of streamlined versions of the formulas. And what I want to do is now modify the distance rectangle formula just a bit to indicate that the height of it for this trapezoid is actually v subscript I. All right. Now, in this formula, I have just a generic v. But what I want to introduce now, because we're going to be putting it all together, we need a little bit more information in the formula itself. I want you to write down the more refined version of it, a little bit more precise, v subscript I. Now, this is something that you can use for any coordinate. So if you're accelerating along the x-axis, you'd have an x component, the initial x velocity value. The initial left to right, if it's going left, it'd be a negative 2.5 meters per second or something. If it's going right, positive 7.5 or whatever it happens to be. But you could use it for, and we're going to use it today, for vertical motion along the y-axis. Okay, so we're going to add a little bit more information to this formula, but here it is. I mean, this is it. This is the change in the x-coordinate. If you're thinking in the x-coordinate axis, then yeah, VIT plus, and that's just the sum of the distance triangle and the distance rectangle. In other words, the trapezoid, the full trapezoid is, a little bit of triangle and a little bit of rectangle. No great shakes about that. And what we're going to be doing today is applying that technology to the concept of free fall, because we've got it all now. All we got to do is kind of think about free fall, and we're going to follow Galileo's lead, and we're going to assemble the free fall version of this, and it's going to look really sweet. All right? Now, any questions about this analysis of the distance trapezoid? Because that's what we do. Whenever you break something apart into smaller pieces, that's called analysis. And when you put it all back together, that's synthesis. So any questions? Yes?
So we're not going to be using the distance equals VT for this segment?
No, we're going to be using it, but we're going to use the distance rectangle technology, but it's going to look a little different. But it's basically still the same idea. It's a distance rectangle. Yeah, it's going to be more refined, and it will be. See, this one is the way that we've got it set up now. This is for a distance, a delta x. But if you're trying to figure out a position, i.e., the x, y, and z coordinates, you got to be a little bit more precise, and we're going to do that this morning. All right. So now we're starting with, and we're in chapter 2 now. So, in matter of fact, you should consider it a homework exercise or a homework assignment, in addition to homework 3 in web courses, just to read chapter 2. It's a fairly short chapter. We're going to be talking about it today. So that'll back up what we talk about. And this is one of the key decisions that Galileo ever made. He said, I'm going to use free fall as my prototype for all and sundry accelerations. Now, there's all kinds of accelerations that aren't vertical. Like if you're in a Ferrari, you go 0 to 60 in 6 seconds or whatever it happens to be. That's a horizontal acceleration. And there's a spacecraft, a launch out at Cape Kennedy or Cape Canaveral. And so that's a vertical launch. But we're going to be doing free fall as a tool because Galileo was convinced that it was the simplest and the easiest to use. And he felt that the book called Nature, or the universe, this grand book called the universe, had a lot of stuff that could be expressed or was best understood in the simplest terms and with the simplest geometric figures and so forth. And an example of that is the distance polygon. Pretty simple, a rectangle and a triangle. That's fairly simple. And I'll tell you one thing, when we're working on really fancy quantum field theory, black holes and stuff, we're doing those trapezoids out the wazoo. So it's this whole idea of starting with something simple and keeping a simple view of it is very productive. Now, here's what Galileo, he made a lot of observations. And there has been scuttlebutt for the last, century or so, based on some French guy who was convinced that Galileo never did the Leaning Tower of Pisa experiment. But now people, scholars of Galileo, smarter than me, are convinced that he actually did that experiment, although he didn't write it up in any of his books. It was in his notes and stuff. And unfortunately, a lot of his writings were destroyed. Like his daughter was a nun, and she lived in a convent, and they wrote letters. I mean, they didn't have telephones. Galileo's daughter, her name was Celeste, Marie Celeste, and they wrote letters back, just lovely. But the only person that we have the letters for are the ones that she sent to her dad. The ones that he sent to her didn't survive. And so we don't have any of those, but we do have his. And unfortunately, but anyways, guys that have studied his papers, as many of them as we have, think, yeah, he did it. And his assistant, toward the end of his life, his assistant, who later became his biographer, was convinced that he had actually done this at the Leaning Tower of Pisa. Anyways, so the famous experiment is you drop a cannonball and a musket ball. So a musket ball is going to be, maybe half an inch or so, pretty big, but not as big as a cannonball. Cannonball is going to be about as big as your fist, or maybe a little bit bigger. And do they drop at the same rate, or does one of them drop more slowly? And he was convinced that they fell exactly in the same pace and stuff, and landed pretty close to the same time. There was air resistance, and he could see it, but he said, okay, if you ignore air resistance, they're going to fall at the same time. So he observes a stone initially at rest. See that? Have you guys written this down? Did you write down this quote from Galileo? I observe a stone initially at rest. Isn't that one of our uses of the distance triangle? That's one of the conditions. Initially at rest. Falling from an elevated position and continually acquiring new increments of speed. That means it's accelerating. So his idea was, if something's accelerating, and he said free fall is accelerating, it's continually getting more speed as it goes down, faster and faster. Okay? He further said, if we now examine the matter carefully, we find no addition or increment more simple than that which repeats itself always in the same manner. And he was able to make experiments, not just with the Leaning Tower of Pisa, but with ramps and so forth. Question? Nope, go to YouTube and pencil it in. Remember, we're going fast through these notes, and but it's going to be in YouTube in the afternoon. You can pencil in the rest of it later. Or if we dismiss early, you can come up and check it. Okay. So his conviction was, and after doing experiments, that in free fall, you always get the same amount of speed for every increment of time. No addition or increment more simple than that which repeats itself. So repeating means over a period of time, always in the same manner. Now, he did not have the metric system, but we're going to do a little table of metric system measurements here. So here it is. We're going to drop from rest and start the stopwatch. So this is like, now this really is a myth. I mean, Galileo wasn't around. He spoke in Italian for one thing, not English. And he didn't have a stopwatch, but he was able to make time measurements and stuff with pendulums and water clocks and stuff like that. So it starts from rest. Now, go ahead and make a table, okay? And you're going to need 4 or 5 rows below this one, all right, because we're going to do several seconds. But at the first second, when you start the stopwatch, It's at rest. So velocity is 0.0 meters per second. But then, if Galileo had been using the metric system and measured the speed after 1 second of straight down free fall, he would have said, all right, my downward speed is 9.8 meters per second. Now notice here, you guys, I don't have a minus sign because I'm narrating and I'm saying that this is a downward speed. Now I don't have the word velocity up there. If I did have velocity, I'd have to use a minus sign or use the word downward. But anyways, the downward speed, 9.8 meters per second. And if you were to go to the library and your friend had a radar gun and you could gun the, an apple or a water balloon or something that you drop over the edge of the top floor, the roof of the library, after 1 second of free fall, it'll be going at 9.8 meters per second downward. Now, here's the second increment of speed. In the next second, another 9.8 meters per second of downward speed. And that's how Galileo found that gravity works. And knowing that, he was convinced that therefore gravity was the simplest acceleration, simply because you acquire 9.8 meters per second for every second of free fall. There's time t equals 3 seconds. All right? Now, he was probably measuring in, I don't know, cubits or something like that, not meters. But if he had been measuring in meters and seconds, this is what he would have measured. 4 seconds, another 9.8. Now, that's a big, long drop. All right? But that is how gravity works. So just put etc. down below that. And the note that the direction is downward. And this is why he said that the increase repeats itself always in the same manner. In other words, here's your money quote. All right? If you're trying to take down notes, here it is. That the increment always repeats itself, always another 9.8 meters per second of downward speed. Now that's what he found to be the case in the measuring system that he had in his day. All right, and he used ramps and he used the Leaning Tower of Pisa and probably used his kitchen table. I read a couple biographies of Galileo over the summer. A very interesting guy. Kind of a character, but smart as the proverbial whip. All right. Now those are the concepts in free fall, and my wonderful students, this is the free fall acceleration pretty much anywhere you can go on the surface of the earth. From the top of Mount Everest to the bottom of the Mariana Trench, if you're in a submarine, and you drop something, it's 9.8 meters per second for every second of free fall. Now, the way that we express that compactly is this. We give it its own symbol, G, for gravity, on the surface of the earth, and we just write it this way, 9.8 meters per second per second. In other words, for every second of free fall, give yourself another 9.8 meters per second of downward speed, if you're on the way down. Now, if you're on the way up, you lose that much. And we'll talk some more about that. Now, here's a more compact, if you've read chapter 1 and into chapter 2, you know that this is a more compact notation for an acceleration, 9.8 meters per second squared. But a lot of times on an exam, okay, I'll write down an acceleration as, so many meters per second per second. And so it's the reason I do it on exams sometimes is because I don't want to use an exponent, a second power, because it bloops up the exam software. So I write it per second per second. But it's the same as meters per second squared. All right, now let's look at the velocity graph and the drop distance concept. So here's your velocity graph. If you start from rest, okay, that's right here at the origin of the two coordinates. Okay, now it's dropping, so now this is a velocity graph. and we have negative signs to indicate downwardness. In the previous table, I put the word downward at the bottom of the table. Okay? But now, on this graph, on that vertical axis, I don't have anything up on top because it's not moving upward. I mean, although I could have something that, if you throw it straight up and then straight back down, you can get velocities up here. But for just a straight drop from the top of the Tower of Pisa, from the top of the library, what'd be cool is to go to you couldn't really do it, but to go to the water tower. I think that's, or maybe, you know what? Has anybody noticed if the big, I think the Libra parking garage, that's pretty much the biggest one on campus, isn't it? I think, and it's got 6 levels. So the roof is 6 levels up. My question, I'm going to have to verify this tonight, is the roof of Libra parking as tall as the water tower or taller? I'm going to have to check that out tonight when I go home. Anyways, it'd be kind of cool to get to the top of the water tower or the top floor of Libra and drop stuff off the side. And if you did, your velocity graph would look like this, continually acquiring a downward 9.8 meters per second. Now the distance, drop distance, we know how to do that. It's the area of this rectangle. It's below the x-axis, it's below the horizontal axis. So we interpret it as a negative number, and that's cool. You're going from a positive height to a lower height. From the top of the Leaning Tower of Pisa to the bottom, from the top of Libra Garage to the bottom. So that's a little bit lower. So if you start at the top, if the 6th floor of Libra is your 0 in the y coordinate system, then you're going to go to a lower number, and at the ground level you'll be some negative number of meters below the original position. Anyways, delta V, that's the vertical part of the distance triangle. And delta T, that's the horizontal part, as before. Okay? And this is using the symbol G as a specific symbol for the acceleration due to gravity at the surface of the Earth. Now, if you're up there in the space shuttle, or the International Space Station, G is a little bit smaller up there, but at the surface of the Earth, it's right about there, 9.8. So this is the drop distance formula. All right. So if all you care about is how far something drops, this is what you do. If you care about its y coordinate, whether it's up or down, then you have to be, as I said, you have to be a little bit more precise, and we're going to get that one. But just for figuring out, how far something has dropped, yeah, this is fine. So G is 9.8. And T squared, of course, is whatever. In this, it looks like 4 seconds, quantity squared, et cetera, et cetera. So let's do an example of the drop distance formula from Lord of the Rings. And I just happened to get from a friend this morning the extended version of the Fellowship of the Ring DVD set. So I'm going to, hopefully I'll be able to watch some of this week. But if you recall from the first movie, Pippin, Peregrine Took, gets into a big problem, and gets everybody into a big problem because he drops something down a well. All right? So here's your calculation. All right, get your clicker out. Okay, for those of you that have not used it before, hold the power, and I know there's a few of you, hold the power button down until it flashes, and then type in BB. And then you'll get the message, go nitro, and ready. Have you got it? Yo. You got it? Good. All right. All right, go ahead and start working on that. Drop distance formula, 1/2 GT squared. Go ahead and do that. And give me your answer to the nearest 0.01 meters. So if your answer comes in, for instance, 22.308, then type in 22.31. And for this one, it's a numeric answer. You have to hit the send key when your answer's complete, when you've typed in what you want. So give me something, point something, to 2 decimal places. And you cutting out of here? Okay. And then hit the send button. And we've got 1 person. 3. All right. Oh, and you know what else? I'm sorry. To get the numbers, you have to use the up and down arrow keys, kind of like on a cell phone. Okay, so it starts you at letter A, and then I think you go downward, don't you?
I think so, yeah.
Okay. You go down, and you'll get I think you get 9, and then 8, 7, and all the way down to 0. Then you get symbols like plus and minus and multiply and so forth. So, all right, good. Hear that clicking sound? That's people clicking in their numbers. On this planet. Now, if I give you, trying to eat my lunch. If I give you another planet, I'll always tell you what the G is for that planet. And the moon is like 1.6. You know, because for if it's obviously something, you know, at the library or the, you know, Libra garage or something, then yeah, 9.8. And pretty much anywhere from the top of Mount Everest, you know, it's gravity's theoretically a little bit weaker up there because you're further away from the center of the Earth, but it's still pretty close to 9.8. And so everybody, and the bottom of the Mariana Trench, the deepest part of the ocean, same. But once you get out in space, significantly out in space, it gets weaker. Question over here. Good? That stuff was so dry.
Oh, man.
And I don't have any water. And I don't have a Monster either.
So
Really
Twitter decided
unfortunate.
to stop working.
Hmm?
Twitter decided to stop working.
Oh, that's good.
So I'm writing notes. And then
Is this on your computer or all?
I don't know because I went to like tweet something and it was like cannot update tweet, like the user does not exist. And then I was like, what? So I refreshed it.
Those
tried again.
jerks.
Didn't work. Logged out. Logged back in. Tried again. Didn't work. So I was like, well, I'm just gonna write it
Could
on a
you
Word
see what you
document
are
and
before
put it
you
up
go?
in discussions, and we'll just see how it works on
Because you use your
Thursday.
cell phone, right? You're using your phone?
No, I'm using my computer, but it's still.
Well, Twitter goes down every once in a while.
Yeah, that's true.
All right, 20 seconds. Boy, that was bad. Got to remember to bring water. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go to the display, the computer display, please. All right, now here's what the results look like. 50.18 is correct. The majority of you got that, but there's a few of you that got other stuff. Wow, look at that, 50.96. 70. Go ahead down the list. The most common one was correct, 50 point. Yeah. Doggone it.
No.
All right, so look at that, 55.18, 10.24, 31 point. Look at that, 50.176. Okay, you gave me 3 decimal points. One person. 51.7. That person at the bottom there dropped a 0. All right. Anyways, let's look at the calculation. Can you switch back to the laptop, please? All right. Now, let's work out the calculation. So all of you go ahead and write it down. I've got it all step by step. So your drop distance formula, if you're just doing a drop distance, you don't have to put negative 9.8, and that's what I've got here. So here are my numbers. For 1/2, I use 0.5, and good old 9.8 meters per second squared, and then 3.2 seconds. But notice my brackets enclose 3.2 seconds, and then the squaring is outside the brackets. So I go 3.2 seconds quantity squared. So that's going to work out to like 10 or something like that. All right. Now, what I normally do when I'm calculating stuff, I'll try to simplify as I go. And what I'm simplifying here is simply 1/2 times 9.8. That's 4.9. All right. That's right here. Okay. And now in my square brackets, there's my 3.2 seconds quantity squared. Now notice that the number 3.2 is squared, right? So that's 10.24. And also the unit of measurement, seconds, is also squared. And that's nice because if I don't have any cancellation here on the screen, but you can cancel it in your notes. Second squared here in the t squared bracket cancels second squared here in the denominator of 1/2 g, that first parentheses. All right? And so you're left with a measurement unit m for meters. Good. That's a distance. And then you still have to do your multiplication. If you do your multiplication, you get 50.176, and then you round it off to 50.18, or whatever it is that I tell you to do on the homework or on the, question. You are allowed calculators, and the calculator that you are allowed is a scientific, any calculator that has a square root key will be just fine. If you have a fancy graphing calculator, it's not going to help you a whole lot, but yeah, you can use it. But you may not use a calculator on your cell phone because you may not have your cell phone out. All right, so you got to get one. It doesn't, but you know they have them for like $15 over in the bookstore. All right. And hey, you guys, start bringing your calculators to class because now that you know, okay, see you, dear. Now that you know how to do calculations with iClickers, we're going to be doing it in class a lot. You know, usually every day we'll have at least 1 or 2 things to calculate. So start bringing your calculator. Question over here.
So you can use the big screen graphic calculators?
You can, yeah. You can use a big graphing calculator if you like. All right, let's keep going. Final comment on this value G. And I've kind of already alluded to it, and that is if we're trying to put together a formula, not for a drop distance, but for a vertical coordinate, a position, then we have to be a little bit more precise. And then we use a negative number for 9.8. But if you're just trying to figure out how far something's dropped, it's assumed that it's downward. So it's like a tape measurement, so you just get a positive number. But if you're trying to figure out coordinates, above the cliff or below the cliff, above the top of Libra garage or below the top, then you have to use a negative number. And we're going to start doing that because now we can put together Galileo's famous formula that I mentioned to you in the context of this baseball diagram back in Lecture 2. Some of the things that we wanted to be able to do, was predict the position of a cannonball in time. And knowing its flight time, be able to figure out how far it goes, how far upward it goes, and how far downrange it goes. And so you can sink your battleship. And you don't want to miss. All right. So now the things in this diagram that we can now handle, we now can handle this vertical increment of distance. Okay, y subscript f up here, y subscript I down here, the initial y coordinate, and the final y coordinate, yeah, we can handle that. We've got the technology to do that. And this one is one where we're going to write symbols, but the g in the formula that we're about to write is going to require a minus sign. But let's get to it. Okay, now, if something doesn't change position, its final position is the same as its initial position. But if it's moving, you're going to have either a distance rectangle or a distance trapezoid. In free fall, it's going to be a distance trapezoid of some kind. All right? So the first thing that you add is the distance rectangle. Now, this is VI, initial speed, and it has an additional subscript, y, to indicate vertical. All right? Now that's so this one will allow you to calculate the position if VIY is equal to 0, or if it's positive. If you throw something straight up in the air, VIY will be like 10 meters per second. If you toss, if you're playing baseball and you get a pop-up straight up in the air from home plate, the catcher's going to get it. But anyways, it's going to have initial upward speed, and you can figure out how long it's going to take to get back to the catcher. And the catcher, and you guys, if you've ever played baseball, to catch something, or you're playing volleyball or basketball or football, you mentally figure out where the ball's going to go, unless you're a total klutz, which, sometimes, I'm not going to say anything, but, some people, they can't catch a barn. I mean, they can't hit a barn with a baseball. They can't catch a baseball for beans, but that's all right. There's other things in life than catching baseballs. And there's other things in this equation, because we also have free fall. How does it show up? Ching! Right there. 1/2 GT squared, just like we were talking about. But now this one, make a note, this is a coordinate expression. It's a position equation, not a distance or drop distance equation. So in this one, yeah, you have to use a minus sign. Matter of fact, in this one, there's 2 places that you want to use a minus sign if necessary. First one, of course, is G. That's always downward, negative 9.8. But the other place is possibly here in VIY. If you're up there on the top of Libra and you see your enemy walking down the sidewalk and you want to totally get them with a water balloon, well, you throw it straight down. Okay? In that case, VIY, if you throw something straight down, is negatory. It's negative because it's going downward. Right? This handles it. All right, so we now have the full technology, and this is something that Galileo figured out. Yep, it all works. And it corresponds to a parabola, as I mentioned in chapter 2. And so we can now talk about Ferraris driving off a cliff and all kinds of stuff like that. Cannonballs. Okay, so a Ferrari driving off the side of a cliff is like half of the trajectory of a cannonball. All right, and I've mentioned that in chapter 2. Now, I want to talk about some more stuff in chapter 2, and that is the argument, and it's kind of a figurative argument, between Aristotle and Galileo about motion. And this is directly applicable to this problem of how do you predict the position of a Ferrari driving off a cliff or a cannonball fired out of a cannon. Right? That's the other half of the motion here. Right? So now in Aristotle's view, there were two kinds of motion for him. That's it. Motion has to be produced by a mover. And all motion is from a force of some kind. Now, he knew that things could be at rest. All right? Now, the way he explained things at rest was they're in their natural location. You know, fire, earth, you know, the four elements of Aristotle, the four classical elements, earth, air, water, fire. And fire rose because its natural place, according to Aristotle, was up in the atmosphere. And earth sank through water because its natural place was below water, according to Aristotle. Now, Galileo didn't think things in the same way. And that's in terms of the elements and also in terms of motion. Now, Galileo said, yeah, we've got forced motions. Gravity's one of them. But he said there's, get back here. He said, yeah, you've got some forced motions, but you've also got unforced motions that do not accelerate. All right? So you have an unforced motion where you're not accelerating, so you're neither slowing down nor speeding up. And so that describes rest, because if you're at rest, you're not slowing down, you're not speeding up. But Galileo said, we've got this possibility, an abstract possibility of being in constant motion, at constant speed, in a constant direction. Now, Aristotle didn't come up with that, but Galileo did. All right, so let's keep talking about this in terms of the Ferrari driving off a cliff. Now, this is how Galileo thought about it. He thought, and he wasn't thinking about Ferraris, of course, but if you have something moving on a horizontal, frictionless plane, so that's kind of idealized, kind of hypothetical, friction, because everything has friction that we can make. But, there's some things that are less friction than others. And so Galileo said, all right, let's think of something hypothetically that has no friction. And it's a plane, it's horizontal. And he said, I know for a fact that it's going to be indifferent to being at rest or in motion if it's flat, if it's horizontal, and if there's no friction. And if it's in motion, it's going to persist at constant velocity in the same direction until it reaches the edge of the plane. And then he said, it's going to drive off the edge of the cliff, and then you've got some free fall action. Now, Galileo, he was able to prove this to be the case. He was able to separate the motion into horizontal whatever's happening on the horizontal plane, this frictionless, mythical, hypothetical plane, and whatever happens to free fall. So he said, you're going to get a mixture or a combination of both motions. And he proved it using his idea of ramps. So let's go through this proof, because it's pretty important. All right, now, according to you and Aristotle, the object on the horizontal plane will only move if it experiences a certain amount of push force. Now, my reference here is to page 27. I believe that's still a good page number for this. All right. So Aristotle would say, okay, fine, you're on a horizontal plane, constant speed, but you've got to have some kind of a push force or a pull force. Right? So Aristotle, he was all about, like for Aristotle, an arrow flew through the air because the air moved behind the arrow and pushed it from behind. And therefore it went further. And the arrow and the air that was in front of the arrow before now moved behind it again and pushed it and kept it going. All right, so here's his car. And Aristotle says, all right, let's say that this car needs a little bit of push force. So let's say 0.02 metric units of force. All right. And Aristotle was perfectly happy with a constant velocity. He just said it requires a force. And if you're at the grocery store pushing carts, grocery carts filled with Cheetos or whatever it is you're buying, then you know that you if you push it and let go, by the end of the aisle, it's going to either crash into something or it's going to come to a stop. So if you don't want it to keep going at constant speed, you got to push it all the way down the aisle. And so Aristotle was thinking in those terms, and it wasn't bodacious. I mean, it wasn't like he was a jerk, because that's the way that's what he observed. All right. So let's refine this picture. Okay, so I'm going to move it up here a little bit. Okay, so there's my push force, 0.02 metric units of force. And this car is going to have a weight force. All right? It's going to have weight pulling it downward to towards the center of the earth. All right? And Galileo knew that. And so he used his idea of forces and ramps and stuff. And he said, look, Professor Aristotle is very nice, but this car has a bit of a weight force. And let's just say for purposes of conversation that the weight force of this car is 0.100 metric units of force. All right, so give that one, and it's 5 times bigger than the push force. So Aristotle says, yeah, it's got to have a push force of some kind. And Galileo says, all right, okay, Aristotle, it's also got a weight force. Let's say that it's 5 times bigger. Right? So make your W arrow, your weight force arrow, 5 times bigger than the push force arrow marked P. And my sketch, it's exactly 5 times bigger. All right? So Galileo says, yeah, all right, Professor Aristotle, I'll take you. I'll take it, and I'll add this weight force. It's going to be something. Let's say that it's this big. Now, let me copy the weight. Galileo said, all right, let's copy the weight forces. All right, and let's park them over here. There they are. Okay, so there's the weight force and the push force. And Galileo said, all right, use the size of those two forces to design a ramp of exactly this shape. All right? So now try to copy a right, or make a right triangle. And here's your right triangle there, of exactly that shape. So in other words, in this example, we're thinking of a ratio of 5 to 1. So 1 unit of height and 5 units of slant. 5 units of hypotenuse. And my diagram is exact. I've done it very carefully. So Aristotle says, yeah, okay, good, nice. 0.02 newtons for this baby to keep it at constant velocity. And Galileo says, yeah, okay, good. And it's got a weight force of 0.100 newtons. And I'm going to use that to build a ramp. Now, why did he build that ramp? The ramp with hypotenuse ratio, height to hypotenuse of 1 to 5 is the exact shape for which the force that pushes something down the ramp has exactly the size of P. So Galileo says, yeah, okay, for this car, I can design a ramp. And the amount of gravity pushing down the ramp, so if you put something on a ramp, gravity is going to push it down the ramp. You know, you release a ball or, you know, a wagon or something, and it's going to go down the ramp. Okay, so there's a little bit of gravity. Most, you know, like for this one, it's a pretty shallow ramp. It's not very steep. But it's going to get a little bit of push from gravity. And in this case, it's exactly the same ratio as the shape. All right? So Galileo says, all right, ratio 5 to 1, 1 to 5. My push from gravity down the ramp is 0.02 metric units of force. All right? And so Galileo said, all right, smart guy, Aristotle, you think 0.02 newtons is what it takes to keep something going on a plane, a horizontal plane, but in reality, that's the push force of gravity going. So you're overestimating Aristotle. 0.02 newtons is what you need to do. Or think of it this way. To push upward, to keep something on the ramp and not fall downward or not slide downward, you've got to push with exactly that amount of force upward, up the ramp, all right, to balance the forces out. And Galileo said, look, if you push force of that size will do on a ramp. Flat plane, you don't need that much. Horizontal plane, no. 0.02 newtons. You don't need that much. You're overestimating. So in other words, a flat plane, whatever you say, it's going to require less than 0.02. Because for an object of this weight, a ramp of 1 to 5 disproves Aristotle's conjecture. So Aristotle could say that okay, maybe it's 0.01, or maybe it's 0.005, or 0.002, or some smaller number. But Galileo says, dude, no way. No matter how small you say that the push force is that's required for this car to go across a horizontal plane, I can build a ramp that disproves you. In other words, Aristotle, you're busted. So Aristotle's philosophy that you could not have constant velocity motion for any reason without a push force is wrong. And Galileo showed that this state of motion, which we sometimes call the inertial state of motion, is possible and has to be accounted for in your study of motion. Now, the reason that this is important for us is because the Ferrari that drives off the cliff, it doesn't have any force on the top of the cliff before it drives off. It's on a mythical, hypothetical, frictionless, horizontal plane, and it doesn't need any force. It's happy to cook along at that speed until it runs out horizontal plane. And Galileo said, all right, once it leaves the plane, the only thing different now is a downward force. So the horizontal motion is going to stay the same. The only change is the vertical motion. All right? So let's get to it. An object with no forces acting on it will stay in a state of motion at constant speed and constant direction. And this actually became Sir Isaac Newton's first law of motion. So let me see if I can restate it. And you'll be able to look in chapter 2, you'll be able to look and see why the equation that we just derived, yf equals yi plus viyt plus 1/2 gt squared, all that boils down to the equation of a parabola, and which is the exact arc of a baseball or cannonball or anything else that's thrown. Half of a parabola or a semi-parabola is the arc of the Ferrari driving off a cliff, or anything that rolls off a cliff, or goes straight off a cliff horizontally. And so that whole idea of separating the two motions into an x motion independent of the y motion, let me repeat that. The whole idea of separating the x or horizontal motion independent of the y or vertical motion is something due to Galileo. Aristotle would never have permitted it. He had all kinds of elaborate statements about motion, but that's a statement he would never have done. But Galileo said, no, this is the way you've got to look at it. Because if there's no gravity, it's just going to keep cooking along. And gravity only acts vertically. So all you have is a change in the vertical part. The horizontal part's just going to keep cooking along. All right, now let's look at Sir Isaac Newton's laws of motion. We'll start with that. And we'll keep going with chapter 3 on Thursday. But let's look at the first law. And Newton's first law of motion is basically, it's called the law of inertia. It's basically the finding of Galileo that an object retains a state of rest or its state of uniform straight line motion unless acted upon by an unbalanced force. All right, now an example is an apple in an apple tree. An apple, so there's some apples there. And Sir Isaac Newton is famous for the apple tree that, the apple that fell on his head by which he discovered gravity, supposedly. Another one of these things that some people think didn't actually happen. So if you think of an apple attached to the apple tree, or an orange, the stem is attached to the branch and attached to the apple, and it pulls upward, and then gravity pulls downward on the apple, so it hangs below the branch, usually. All right? And everything's copacetic. Those two forces balance. Everything is nice. So the apple is just kind of sitting there and, getting bigger and sweeter and so forth. But if the stem weakens, and the stem of an apple can weaken, same for citrus. If it dries out, it'll get brittle. And then the wind comes, and if it's brittle and the wind is strong enough, it'll knock the apple down and off the tree, and it'll fall on Sir Isaac Newton's coconut, and then you discover gravity. So if the stem weakens, the balance will fail, and it'll fall downward. All right, so that's an example, of balanced and unbalanced forces. If the forces are balanced, everything stays at rest. So this is an example of staying at rest. All right. Now I'm going to give you a second law of constant velocity motion. All right. So let's look at this diagram. Okay. In the first one here, and there's a discussion of this in chapter 3, the UCF shuttle bus. If you're on a shuttle bus and it's moving, if it's moving forward and you're standing in the aisle, and you're holding up your hands, look, Ma, no hands, okay? And you're standing in the aisle, and all of a sudden the driver brakes or speeds up, you're going to take a tumble, or you're going to reach out, And so if he speeds up, okay, your state of motion is going to tend to be a little bit slower, so your body's going to try to be behind the bus or lose pace with the bus, i.e. you fall backwards. If he slows down, your body, except for your feet, is going to tend to go in the same, 25 miles an hour. So if he slows down to 20, the bus and everything attached to the bus is going 20, and you're still going 25, so you pitch forward and you face plant in the aisle, right in front of your friends. No good. All right? Now, same thing over here in picture. Let me get my cursor over there. Cursor in picture B. All right, so this is the bus turning. All right, so if you're standing in the aisle and your hands are up, look, Ma, no hands, okay? And he turns to the right, your feet are on the floor, but the rest of you is going to try to keep going straight. So what happens is you bump into the person on the left of you. All right? You got to stabilize yourself laterally. All right? So if he turns right, he's easing off to the right, and everybody else that's buckled in or seated is going right, but you're going to keep going straight ahead the way you were before he turned, and you're going to bump your left hip. If he turns to the left, okay, if he turns the other way, you're going to bump your right hip into the seat next to you. All right, so here it is, A and B. All right, the bus moves forward, you lurch backwards. The bus slows down, you lurch forward. So you have to stabilize yourself. And you guys do this. I mean, if you're in the aisle, if you're standing, which I understand is common, trying to get up to campus on the UCF shuttle buses from some of the off-campus apartment houses and stuff. I hear it's kind of pitiful. But anyways, if you're out in the aisle, you got to stabilize yourself, or you're going to fall in somebody's lap. That's no good. Crush their computer or something. So that's the first law. That's the law of inertia. It's discovered by Galileo. And Sir Isaac Newton used that concept as his first law. Now here's another picture. Just think of a football player throwing a forward pass, and it arcs up into the air on a parabola. And it's got some, it's got some spin as well, so it's a good tight spiral. And then the guy catches it. But the interesting thing about this is a good diagram because it shows that the horizontal arrows here are not changing. They're all the same size. But the vertical arrows, the vertical component of the motion, the vertical component of the velocity is changing. As a matter of fact, it's upward here in the first half of the throw, and then on the second half of the throw, they're starting to go downward because it's going down to the receiver. All right? Now remember this diagram when you're tackling your homework tonight. It'll start in just a few minutes. And let's dismiss there. We'll talk about, but definitely read chapter 3. We're going to talk about second and third law Thursday. Homework 3 is due Thursday. You're dismissed. It's a good place to dismiss.